Alright, in this video we're going to look at how we use the shell method to find volumes of solids. The shell method works a little bit differently from the disk and washer method. Instead of having a strip that is perpendicular to the axis of rotation, we're going to be working with strips that are parallel to the axis of rotation. That's the first big difference. The second big difference is in how they're calculated. There's about a page to a page and a half of information about the development of the shell method in this lesson that you guys can go ahead and read through at your leisure. You know, we talk about where the shell method comes from and how we develop the general formula. But in general, the formula for using the shell method to find a volume of solid generated by revolving around the y-axis is that it's going to be 2 pi times the integral from the x-coordinate of the left endpoint to the x-coordinate of the right endpoint. And the integrand is going to have two parts to it. The first is going to be the distance from the shell to the axis of revolution, and the second part is going to be the height of the shell, which we determine by taking the height of the upper boundary minus the height of the lower boundary. Alright, so let's look at how we do this with this first example. And in this first example, we're going to use the shell method to find the volume of a solid generated by revolving these two curves around the y-axis. So we've got y equals x squared minus 4x plus 1, and y equals negative x squared plus 6x minus 4. So those are our two curves. We'll go ahead and look at this in a standard window. And there's our picture of the two curves. Just going to jot a quick sketch down of that. We've got a parabola and another parabola. It's something like that. That's our region excuse me, that we're revolving around the y-axis. Now, I mentioned that the big difference between this and the disk and washer method is that our strips are going to be parallel to the axis of rotation instead of perpendicular. So I've drawn in a sample strip to develop this. In order to find this volume, we're going to take 2 pi times the integral from the left endpoint of the region to the right endpoint. So we can go ahead and find those points of intersection now. And those are going to be in terms of x. When we're using the shell method, the variable that appears in our integrand and in our limits of integration is the opposite of the axis of rotation. So I'm going to go ahead and find those intersection points. First one is at 0.563508. 0.563508. I think we ended with 2 3's there, 2 3's. And the other limit of integration is going to be the intersection point at the right hand, which is somewhere around 4, I guess. 4.4364917. Okay. Now, the component parts of our integrand. First thing we need is the distance from the axis of rotation to the shell. That distance right there. And since we're revolving around the axis, that distance is just going to be the x-coordinate of wherever this shell is. And so we'll put x into our integrand. And the other part of our integrand is the height of the shell. So we want to take wherever this point is minus wherever this point is. And so all we're going to do is subtract the two curves. The one that opens down is the upper one in this particular problem. And so we're going to go ahead and subtract those two. And this is going to give us the volume of the solid when we revolve this region around the y-axis. So why use the shell method when we already could have done this using the washer method? Well, This would have been very complicated using the washer method. We would have had to complete the square to solve both of these equations for x and get x as a function of y. And then we would have had multiple integrals because of the differing boundaries on the region. Whereas with the shell method, we can do it all with one integral. And we don't have to go through the process of completing the square to calculate those equations. So we're going to have 2 pi times the integral of x times the quantity negative x squared plus 6x minus 4 minus the quantity x squared minus 4x plus 1. There's that quantity, there's that quantity with respect to x from 0.5635083 to 4.4364917. There's a parentheses. Uh-oh. I think I need another parenthesis in there, maybe. X times, no, I put one too many parentheses in here. There's this one right here. And we get 304.183 for the volume of this solid. All right. On to example 2, we're going to do the same thing. We're going to find the volume of the solid generated by revolving this region bounded by these curves around the y-axis. So we've got y equals 4x minus x squared, and also the line y equals 4, and the line x equals 0. So we've got a parabola, 4, and the line x equals 0. So we're looking at this region right in here. Okay? Now, there's a sample strip. The distance of the shell is again going to be x. And then the height of the shell is the horizontal line minus the parabola. And my limits of integration are going to be from 0 to wherever this line and this parabola intersect, which I'm pretty sure is where x is 2. Yep, where x is 2. All right, and so now I can calculate the volume of this solid. I'm just going to go ahead and take 2 pi times the integral of x times quantity 4 minus quantity 4x minus x squared. Close that quantity. Is that quantity with respect to x, 0 to 2. And I guess I really could have integrated this by hand if I wanted to, but I didn't really want to. And so we end up with a volume here of 8.378. All right, so that's how we can use the shell method to find volumes of solids revolving around the y-axis. We'll look at the same concept only going around the x-axis in the next video. Hope to see you then. Have a great rest of your day.